Hello everyone and welcome to this talk. Jim Newton and myself will present you today our portable, simple, embeddable type system inspired by Common Lisp. Very briefly, our goal is to be able to type heterogeneous sequences such as lists of arguments of various types. Here it could be integers or strings. In order to explain why this issue is relevant, I will now let Jim perform a brief closure demonstration.
In this demo, we're going to talk about a project called Genus. Genus is implemented in Clojure, and Genus is a type system which hosts some of the Java types which come with the fact that Clojure is implemented on the JVM. But it extends the Java types in a way which should be familiar to many Common Lisp programmers. Let's start by looking at how functions are defined in Clojure. So a function definition in Clojure can have multiple implementations, one per arity. If I define the function foo like this, and I call a function with one argument, then since it has one argument, the one arity clause is selected, and this expression is evaluated with x bound to 1. And we see that the return value is correct, x1. If we call the function with two arguments, we see the second clause is selected, and x and y are bound to 1 and 2, and the expression is evaluated. Variable binding in Clojure supports type hints and destructuring, and variable arity functions are no exception. We can specify destructuring syntax into the lambda list, so expecting two arguments, one which goes into x and one which is destructured into u and v. We try to define this function, and we have a compile time error because we specified two functions with the same arity, and that's not allowed. So every element or every clause in the function definition must distinguish itself from the other clauses by arity, even if you might intuitively think they're distinguished by some other mechanism. Given that constraint, we can specify so-called type hints. So we can specify that x is expected to be Boolean, and we can specify further destructuring for particular elements of the lambda list. If you call this function with one argument, then the first clause is selected even though one is not of type Boolean. And if we call the function with two arguments, the second of which is destructible into u and v, then the second clause is selected. If we call the function with two arguments, the second of which is not destructible, we get a runtime error. So error at function call time. So the thing to realize about that is the clause selection of the variable arity functions really is only done as a function of arity. The type hint is ignored, and the dispatch is ignored as per the clause selection. It's not really defn which does this work. It's really the lower level operator fn. Fn is the way to specify anonymous functions, similar to lambda in Common Lisp. And the syntax is exactly the same as you would expect. Fn can take one or more clauses, each which specifies a pairing of a lambda list to a function body. I'd like to introduce a macro called dsfn, which stands for destructuring function. So it's designed to be syntactically similar to fn, the normal anonymous function definition facility, except that dispatch will be based on arity, on destructuring, and also on type. If we take a look at this call, If the function is called with one argument, then it dispatches, as usual, to the first clause. If we specify an argument, first argument which is a Boolean, and a second argument of anything, then it dispatches to the second clause. And if we specify a first argument and then some other argument which can be destructured into an x and a y and a z, then we see the third clause is evaluated. If the second and third clause both apply, then the first clause, if the second and third clause both apply, then the second clause is the one that's selected because precedence is given to the leftmost or topmost clause. So until now, we've only talked about very simple types corresponding to simple names from the Java virtual machine. We'd like to be able to talk about more expressive types. So there are two genre of types that DSFN is capable of representing. One is the satisfies type, and one is any Boolean combination using and or not of more primitive types. First, why would we want to support the satisfies type? Well, one reason is because Clojure programmers are used to already using a lot of predicates that are built in. So Clojure programmers don't typically reference types specifically by name. It's just not in the tradition of Clojure programming. Rather, there's a bunch of types, a bunch of predicates built into the Clojure core. We see here integer question, which is implemented in terms of particular type names, integer, long, big, int, short, byte, etc. And there's a lot of other types that are implemented in terms of type predicates, odd, even, int, positive int, negative, natural int, and so on. So a Clojure programmer, when faced with the system genus, is very likely to want to use these predicates that he's already been using for the last many years of his Clojure experience. So satisfies gives an interface to those predicates. The user can write his own predicates, of course, but typically they will really want to use these built-in predicates. So the piece of code here asks, is true a value which satisfies the integer question predicate? No, it's not. So the BBB gets evaluated. The other type of type designation, which a common Lisp user is very accustomed to using, are Boolean combinations. So is 12 something that satisfies integer question? Yes. Is it something that does not satisfy long? Well, 12 is of type long, so then this and type 12 is not an element of that intersection type, so BBB is returned. If I use the syntax 12in, which is the big num 12, we see that AAA is returned because the big num 12 does satisfy integer and does not satisfy long. The problem of selecting the most appropriate function for a call site argument list, for selecting that according to a set of lambda lists with metadata, is closely related to the problem of sequence recognition. In fact, we can view the call site argument list as a sequence, a finite sequence, and a set of patterns, one per clause. And each time we're asking the question, does the pattern match the sequence, or does the sequence match the pattern? And select the piece of code for the most appropriate match, if any. The problem of efficient type-based sequence recognition is a harder problem than we are able to address in this particular presentation, in this publication. We'll address that more robustly in a future publication. But for the moment, we want to look at a simpler problem, which is the first step in a sequence recognition problem. And that's the problem of simply how do we implement a sufficiently general but simple type system and embed that in a language such as Clojure. A simpler problem than DSFN is type case. So type case just matches a single value to a set of prospective type designators. If we look at the example, we have a value of 6, and we want to know if 6 is an element of any of the specified types. If not, return the default value. So is 6 an element of the intersect or the union of string and double? So is 6 a string? No. Is 6 a double? No. Otherwise, is 6 both something that satisfies int? Well, yes. And satisfies odd? No. So is 6 something that satisfies int? Yes. Is it something that does not satisfy odd? Yes. Is it something that does not satisfy negative? Yes. So 44 should be returned. And in fact, it is. Here is the macro expansion for the piece of code that we see here. We notice that even though int appears multiple times, odd appears multiple times, that we don't see int question at all in the expansion, and we see odd multiple times, but it never appears in a single branch of the if. So there's one branch of the if which contains odd, and there's another branch of the if which contains odd, but in this case there's only one odd here and one odd here. So any path through this piece of code will only encounter odd question a maximum of one time, and it doesn't even doesn't even encounter the int question. Why? Well, because int question is code which we can inline and resolve much more efficiently than just a type test. In reducing this code, there's several questions that we would like to ask, and in fact we can ask. So we can ask subtype questions. For example, if we determine that the value is not an element of type double, then we know that it's not an element of any other type which is a subtype of double. So we can both factor away any occurrence of double from the else part, and we can also factor away any subtype which is a subtype of double. Likewise, if we know a question of disjointness, if we know the value is double, then from the then part we can factor away double because we know it's true, but we can factor away anything that's disjoint from double because if it's double, then it's not string, for example. So we can factor away every disjoint type from the else part. And finally, the habitation check. If we encounter some type which is not inhabited, which is empty, then we can completely factor away the then part because the then part will never be reached. There's never going to be an object which is an element of that empty type.
Thanks for the demo, Jim. That's a nice type system you have there. Maybe we would like to extend it to other non-Lisp languages in order to reason about the regularity of heterogeneous sequences. Our framework should be able to handle subtype, disjointness, and habitation queries, as you've just seen in the closure demonstration. Our long-term goal that we won't be able to fulfill in this talk, but we will perform the first step, will be to use this simple type system in an automata theoretic recognition flow of regular type patterns. The classical algorithm to recognize regular patterns on sequences relies on a form of labeled graph known as a finite automaton. If you're not familiar with this framework, then this idea is actually rather straightforward. We start from an initial node in the graph. We read the input sequence left to right, moving through transitions and ending up in new states. When we've read the entire sequence, then we check the last state visited. If it is final, represented here by a double circle, then we accept this sequence. If it's not final, then we reject it instead. Our intuition would be to use a finite automaton labeled by types to recognize a regular sequence of types. In order to move through a transition, the current input symbol should belong to the labeling type. The issue here is that two types may overlap. As an example, a float is also a number. As a consequence, the following automaton is not deterministic. If we read an input float in state Q0, then we can either stay in Q0 or move to Q1. Through the use of set theoretic operations, namely intersection and complementary, we can handle overlapping types and design a deterministic automaton. Consider the following example. In order to move from state Q0 to state Q1, my input value should be both a number and not a float. The actual goal of this talk is therefore the following. We will introduce a simple type system known as sets, inspired by Common Lisp, that supports set theoretic operations, so union, intersection, complementation, membership, and inclusion. We will also implement this simple type system in 3 languages. Common Lisp relies on a very interesting type system. In Common Lisp, a type behaves like a mathematical set of objects, so it's merely a set of values amongst all the possible values that can be computed by the language. If all types are sets, then we may try to order them according to the subset relation. This allows us to define a subtype hierarchy on types. Here, as an example, we claim that integer is a subset of number. Float is also a subset of the type number, but since this is a partial binary relation, we cannot compare integer and float. Let us now define our type system formally. In a similar fashion to Common Lisp, we will consider that a type is merely a subset of the set sigma of all possible values. Moreover, we will assume that the host language provides a given set of fundamental types, be it integers, strings, whatever. In order to manipulate these types, we will also need a set epsilon 0 of type designators. A type being a possibly infinite set of values, we cannot manipulate it directly. That's why we will instead use handles or names known as type designators that are matched to a given type. As an example, in the type hierarchy we described previously, the type designators were the following: symbol, string, number, and so on. Starting from these host types, we can define our type system as well as the matching type designators inductively. We will need an universal type and an empty type, whose behavior is fairly straightforward. We also want a singleton type that only contains a single element. We also need a predicate type defined by a Boolean function f. Finally, the union, intersection, and complement types behave as you would expect from set theoretic operations. We want to be able to perform 2 queries on these inductively defined types. The first query is the membership operator. We want to be able to decide whether a given value belongs to a given type. This operator must be decidable. The other query is a partial subset relation that would allow us to decide whether a given type is a subtype of another. Note that this relation may not always be decidable. Note that this simple embeddable type system is not meant to implement that of Common Lisp, although it bears nonetheless some obvious similarities to it. The following types, operators and constructors, are indeed equivalent to these Common Lisp types, logical operators, and functions. You may question the need for this subtype relation. Then please consider the following example. If we want to decide whether the intersection of two types A and B is empty, then this problem is equivalent to A being a subtype of the complementary of B. Disjointness and habitation queries therefore depend on this subtype relation. Unfortunately, these disjointness and subtyping queries may not always be decidable. Therefore, our type system should be able to return true, false, or don't know if the current problem is not decidable. We work around these undecidable instances by performing a long but inexhaustive series of checks in order to answer these subtyping queries. We may try to disprove necessary conditions in order to provide a negative answer, or we may try to prove sufficient conditions in order to provide a positive answer, or we may reduce the problem to a necessary and sufficient condition. Practically speaking, we implemented sets in 3 programming languages. The first one is Clojure because it is a Lisp and therefore logical transition for a theory inspired by another Lisp. The next language is Scala because it runs on the same Java virtual machine as does Clojure. Last but not least, we are working on a Python version, which chose Python because it is a dynamic language that makes different assumptions about types than the 2 other JVM-based languages we introduced previously. That's all, folks. Thanks for your attention. We will now try to answer any question related to this talk you may have.